Um, of course, Liz is in Africa, so she won't be, but she'll be watching these videos. Okay. I hope you guys had a good New Year's and stuff like that. And well, we have 5 months to go now for the AP Chem. So we really be meeting on a consistent basis. Okay. Uh, because we have a lot of stuff to cover actually. All right. Uh huh. Today. Today. Yeah. I didn't want to bother during the time break time and stuff, but now I have the stuff ready, because I need to buy those. I have some of the books, but not all of them. So I'll be buying those books for myself as well. And we'll be actually giving. I'll be giving AP Chem homework starting once the books arrive. You'll have the AP Chem books as a part of the homework. Okay. 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 So let's get started. So we were doing photoelectric effect, the quantum equations. We're gonna be doing. Um, let's see. Okay. You guys ready? Okay. Um, okay. So you did the electronic configuration, so you guys know that one. Uh, have you heard about quantum numbers or wave numbers? And there are four of them: N, L, ML, MS. Have you heard these? Okay. All right. So we have a lot to talk then. Okay. So there are three major atomic theories. Dalton's atomic theory, which we have talked about it. If you don't remember this, this is a good time to study and hopefully never forget it. Then is the Bohr's model. Now you guys know what Bohr's model, right? And the third is the quantum mechanical model. So this is by Schrodinger. So these are the three important atomic theories. So for the Dalton's and Bohr's model, electron was treated as a particle because it has mass. But in the quantum mechanical model, electron was treated as a wave because it has hardly any mass. So what happened was, de Broglie, if I remember right, his name is Antoine de Broglie. No, forgot his name. I keep calling him de Broglie. So what happened was, de Broglie made a comment, and this was his comment. According to classical physics, light behaves like a wave. So, classical physics, light is a wave, which is true for many cases. Then, Max Planck and Einstein said for the quantum physics, light was in the form of a photon, particle. So he said, okay, if light can behave as wave and particle, called the dual nature of light, why doesn't matter behave the same thing? So according to classical physics, matter was a particle. And according to quantum physics now, why matter cannot behave as a wave or an energy. So exactly the opposite concept. Well, that doesn't make sense for many of the things, but for extremely low mass particle like electron, an electron can be treated as a wave because electron hardly has any mass. The mass is 9.1 into 10 raised to minus 28 grams. So hardly any mass. Are you guys with me so far? Did you write down this? Okay, go ahead and write down, then I'm going to erase it and continue the side. I knew that was coming. Okay. Do you have any questions so far? Okay, good. All right. All right. So de Broglie said that if we have a particle that has extremely low mass, like electron, that can behave as a wave, which is fine. So as soon as you say the wave, so instead of electron if thrown, instead of moving in straight lines, electron now is going to move like a wave, like a light wave. If you have a wave, then you have wavelength. So this is your wavelength, famously called de Broglie wavelength. So he wanted to find the de Broglie wavelength of particles which has low mass like electron. So what he did was he used two equations. Very, very famous. Planck's equation, hc or lambda, which we did last time. Then of course E is equal to mc squared. The reason is E is equal to mc squared and E is equal to hc or lambda. Remember, both have energy on the left hand side, so he equated them. So instead of using c, which is the velocity of light, he changed it to v, velocity of a particle or a wave. Because not anything which has mass cannot travel at the speed of light. It may be very close to it, but not equal to it. 1v cancels. So lambda is equal to h or mv. You just switch these two sides. One of the famous equations called de Broglie equation. Imagine this, people don't understand the significance of this. This is the only equation where we have wavelength, which is a wave, and your mass, which is matter, in the same equation. Never ever a energy, a wave, wave, light, and matter would combine in the same equation. So technically speaking, when I throw an electron, according to de Broglie, it's not coming as a straight line, it's coming as a wave, which is three-dimensional. Are you guys with me on this? No, wave is a three-dimensional, right? Wave is not two-dimensional. Wave is a three-dimensional. So imagine this. If I throw this marker at, let's say, Valeria, I'm pretty pissed with her right now. Technically, I'm What's that? Well, Happy New Year, by the way. so, so if I throw a marker at her, I'm not sure whether I'm going to hit or not because it's three dimensional. If it's a part, it's a wave. It's going to go like a wave. So I do not know if I'm going to hit her. But if it's particle, I'm pretty sure that if I hit it in the right direction, it's going to hit her. But it doesn't make sense to think this marker as a wave because it has mass, it's significant mass. But if I bring this mass to extremely low mass, like electron, then yeah, it makes sense. Imagine if you throw a ping pong ball, it kind of curves, right? Am I right? Why? For the simple fact that it has low mass. Try curving a basketball. It doesn't curve as that much. So more the mass, less curves, no less curve it will take compared to something very low mass. So the electron getting treated as a wave has a very good implication, has a very good meaning to it because it's so less mass. This is called the de Broglie equation, and this wavelength is called the de Broglie wavelength. Exactly. Look at this. Look at this. More mass, less wavelength. So if the mass tends towards infinity, lambda tends towards zero. Limits. When lambda is zero, then it's a particle because this becomes zero. It becomes straight line. Makes sense, right? Okay, go ahead and write on this. Cool beats. So then came. Actually, I want to do a problem on this just in case. Um, so lambda is equal to h over mv. Mass has to be in kgs. Velocity meters per second. Wavelength is meters. Of course, Planck's constant is joules second. So what I would like you guys to do is, so let's say I have a basketball, baseball thrown at let's say 95 miles per hour. What's the mass of a baseball? Hold on. What is the weight of a baseball? It's giving the schedule of the games. Oh God. Hold on. Baseball ball weight. Jeez. Okay, 149 grams. So we know something today. Find the de Broglie wavelength of the baseball ball. Yeah, 6.626 times 10 raised to negative 34 joules second. I already told you wavelength is in meters. Oh well, you have to. Okay, the reason you have to do this is you have to convert the joules to kgs meters per second square times meter per second times. Hold on. Force times distance. Well, you have to do the okay. Work is equal to force times distance. Force is mass times acceleration times distance. So kg times meter per second square times meter. So it'll be kg meter square second square. That's Newton. Yeah, Newton per Newton meter. So then that's the joules times second divided by kg meters per second. So second cancels, second cancels, meter cancels, kg cancels, so you're left with meters. Right? Yeah, question? Tell me, let's see. I getting 1.05 times 10 raised to negative 34 meters. So that means it's zero, right? So you should not treat a baseball as a wave when thrown, because 10 raised to minus 34. So it's almost equal to zero. So a baseball is not it does not demonstrate a wave-like behavior, because almost is zero. It's good. So somebody misses the baseball, the batsman misses the baseball, should not say, "Oh, I'm sorry, I missed it," because it's a wave-like property. You with me on this? He's drunk basically at the time. So that's what it is. Cool, right? Okay. Now we take all these things, then go to Heisenberg's uncertainty principle. Uncertainty principle. Have you heard this? Okay. So let me write the equation. You don't have to know the equation, okay? You don't have to know the equation. So what he said was, if a particle is a wave, like electron is a good example to talk about because there's an extremely low mass. Either I know its location with certainty, or its a velocity with certainty, but not both at the same time. So if I know, so delta x is the uncertainty in the location, delta v is the uncertainty in the velocity. Okay, uncertainty in the velocity of the electron. So if the uncertainty of the location is zero, that means I know exactly where the electron is, then I'm 100% sure I do not know its velocity, and vice versa. So either you can know the location or the velocity of a wave-like behavior of an electron, but not both at the same time. That's why it's called uncertainty. We are not certain where they are or what velocity is traveling. You can know one or the other. Make sense? Okay. So that was a direct extension from de Broglie equation, by the way. And Schrodinger took this one and created the quantum mechanical model. In the quantum mechanical model, he treated the electron as a wave. A wave has a wave equation. A wave equation has solutions, multiple solutions. And one of the solutions is called a wave function called psi, psi, it's called psi. So electron is in the form of a wave. Wave can be represented by an equation. This equation has multiple solutions. One of the solutions is called a wave function, psi. But they found out psi did not tell us the whole lot of information. Psi squared did. So what does psi squared tell you? It gives you approximately 90 to 95% chance of finding an electron in a given space around the nucleus. So psi squared is the probability of finding an electron around the nucleus of an atom with a 90 to 95% chance. That's good. This wave function can be explained by wave numbers, or called quantum numbers. So that's how we get to this particular point, is from here. So to explain the wave function, you need wave numbers. And N, L, M, L, M, S are the 4 wave numbers that can help us find the location of an electron. N is like a shell number, has the values 1, 2, 3, and so forth. Called principal quantum number. Principal quantum number. It gives the size and the energy. It gives the size and the energy. As you go down, the energy increases. So third energy shell has more energy than a second energy level, or principal quantum number. L is called angular momentum quantum number. Has the value of 0 to n minus 1. So L has the values of 0 to n minus 1. It gives the shape. It gives the shape. Size, energy, this gives the shape. So if I take n is equal to 1, that's the first principal quantum number. So it's 0, 2, 1. So, and 1 minus 1 is 0. So L is equal to 0, what we call the S subshell or S quantum number. N is equal to 2, the values of L are 0, 2, 2 minus 1. So 0, 2, 1. 0 is S, 1 is P. 0, 2, 1. 0 and 1. N is equal to 3, 0 to 2. Oops. And so forth. Are you guys getting this? What do you mean? One. No. If L is equal to 0, we call it as S. If L is equal to 1, we call it as P. If L is equal to, we call it. So if N is equal to 4, so it has 0, which is called the S, 1, which is called the P, 2, it's called the D, and 3 is called the F. That's how you get the names SPDF. I told you, I know a little chemistry and we never agreed. Valeria, you always said that, right? Remember Zoe, she has said it like 10 times, right, so far? Yep, thank you. See, 2020 is starting out with a good note. People are supporting me. Okay, now comes the ML. ML gives the directionality of the angular momentum quantum number. So it has values of minus L to plus L. So if it's 0, it's minus 0 to 0, it's just 0. So this is ML is 0. It has only one direction because called the spherical shape, because angular momentum quantum number gives a shape. So S is spherical, and you can see the ball in any direction, it looks the same. L is equal to 1, it is minus 1 to plus 1. So it will be minus 1, 0, plus 1. 3 directions, Px, Py, Pz. D minus 2 to plus 2, minus 2, minus 1, 0, plus 1, plus 2. 5 directions. These directions are also called as orbitals. So S orbital, S subshell has one orbital called S orbital because it's the same thing. So S subshell and S orbital are interchangeably used because it's only one thing. But P has 3 orbitals, Px, Py, Pz. D has 5 orbitals, minus 2, minus 1, 0, plus, and they have names too. You don't have to worry about it. dxy, dyz, dzx, dx squared minus y squared, and dz squared. We don't have to know the names. Could you tell me for F, how many directions we'll have? So total how many? So yeah, 1, 3, 5, 7. You're forgetting the 0. So the formula to find the number of directions is 2L plus 1. So you tell the value of L is 3, 2 times 3 is 6, plus 1, 7 because of the 0. Zoe, getting this? This one? Okay, so for L is equal to 3, that's the F, there are minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Seven directions. No, total 7. Okay? So, and ms is called the spin quantum number. Spin quantum number. And it has two values, plus half or minus half. Up arrow or down arrow. You can use that as well. Please remember, up arrow doesn't mean it's plus half. It's just plus half or minus half you can use, or up arrow and down arrow we can use. Either one is fine. Getting it? Okay, we'll talk about it. Did you guys done writing this? No, take time because this is important. If you want to take a screenshot as well or whatever. Yep. Yep. Oh, I didn't even say ML stands for. ML stands for, hold on. Magnetic quantum number. Yes. Okay. You can try that for 5, n is equal to 5. Just try the whole thing. Just as practice. We don't have to worry about it, but it's just. Yes, because it's saying that in the fifth shell, in the fourth shell, you have all of them. Okay, so when you do n is equal to 4, right? We do 0, 1, 2, 3, right? When you do n is equal to 5, you have to do 0, 1, 2, 3, 4. Well, after this, it follows alphabetical order actually. You don't have to worry about it. G, G. Yep, yep. Once she's done, we'll get started. Okay, tell me, uh, what are the values of ML? Yep. Good, good. So once you get that, yep, because you have the negative and the positive. Make sense? Okay. Alright. Okay. Let's go now. So we did, now we're gonna take all these information and start combining them. Okay? So we have S P D F. S has one orbital, P has three, D has five, F has seven. This is the PX, PY, PZ. This is most commonly used, that's why I'm using that. In each orbital, one orbital, that's these, okay, 1, 3, each, you can have a maximum of 2 electrons. Go ahead, write down these things. Done? If that is the case, tell me how much each will hold, each subshell will hold in terms of electrons. Mm-hmm. So it'll be 2, 6, 10, 14. Now you know how these numbers are coming out, right? Okay, next. Okay. Assigning wave numbers. Okay. And this is something that you need to listen up. This is important. So let's say I give a 4D electron. Please listen up. This 4 represents the N is N value, 4. D, as we just did, 0, 1, 2, 3. 0 is S, 0 is S, 1 is P, L is 2, L is 3. We don't have to worry about after that. So for D, L is equal to 2. And for 2, you know the ML values is -2, -1, 0, +1, and +2. So you can pick any of these. And for MS, you can pick either +½ or -½ So tell me, for a 4D electron, how many possible combinations we can have. So these two are fixed. You cannot change these things. So we can have 5 of these, right? Any of these, and 2 of these. So how many we can have combinations? Yeah, that's how they got the 10. Does that make sense? Okay. So if they ask you to assign a wave number, this is what they are asking for. For ML, you have, of course, you have to mention ML. You can pick any of these ones. For MS, you can pick either half, plus half, or minus half. So So one of the example I can write for one of these will be 4, 2, minus 2, minus half will be one combination. Has, exactly, that's called the address of an electron. This is called address of an electron. Exactly. Now you can, I'll tell you, explain you why one orbital can only hold a maximum of 2. Because if one is plus half, the other one must be minus half, because no two electrons can have the same exact address, called Pauli's exclusion principle. So what is Pauli's exclusion principle? No two electrons can have the same 4 wave numbers. Got it? Okay, now you guys write the 7p address. At least write 2 possible address of a 7p electron. Okay, I told you, right? It will be 4, 2, minus 2, minus half would be one address. Okay, each one of you say one address. So no, this is how you say 4, 2, minus 2, minus half. That's how you say. But I gave a 7p electron, not 6, right? Okay. Okay, what do you got, Zoe? No, L is fixed by here. That's the main thing for L is always the one that never changes. Because if it says 7p, p is 1 for L. guys getting this? Do two do 2s electron. Yeah, tell me. Can ML be 1, Valeria, when L is 0? No, but and if no, but L is 0 for s orbital. If L is 0, ML is minus L to plus L, 0 to 0. Mm. So it'll be 0 0 plus half, or 0 sorry, 2 0 0 plus half, or 2 0 0 minus half. This is the only choice you have. You guys got it? Feeling better now? Because I've seen this question pop up a lot. Okay. All right. Now, what I'm going to do is I'm going to actually give you an address, and you should tell me whether it's a valid address or not. You can call UPS if you want to find the address verification. Is this a valid address? Don't answer it. First figure it out, then we'll see. Mm-hmm. Okay, but question is not what it is. Question is, can it be valid? Then, yeah, tell me, correct or wrong? Yes, it is valid. Because if n and L has no relation, if this is seventh shell, this is fifth subshell means 0, 1, 2, 3, 4, 5. That means ML can have -5 to +5, any of those values, and MS is -half or +half. So this is valid. Valeria, make sense? Okay. Valeria, what's the answer? Mm-hmm. What's wrong? Yep. Good. So, not valid. Is getting a good idea now? Yes. 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 Okay, well, let's see. Let me see what if this is valid or not. How about this one? Tell me, Zoe. No, not valid. This is wrong, because if this is n, right? L has the value of 0 to n minus 1. So 0 to 5 minus 1 is 4, so it cannot be 5. So you always read like this. If this is never a problem, but this can be a problem based on this value. That's why this is okay, but this is not okay here. Good. This completes chapter 6. Chapter 7, sorry. 6 we still is the calorimeter, the thermochemistry. I'm gonna combine with something else. But now we are gonna move to chapter 8 is very small. 9 is you guys are pretty good with 9, 10 and stuff. So hopefully within a couple of weeks we should be done with Chem 1 and start with Chem 2. Okay. Yeah. Okay, good, because that's a pretty important meeting. Um, are you guys available tomorrow? I can meet tomorrow at 8 to 9. Till what time? Okay. No, I cannot do till at least till 6. Okay. Okay, we'll figure out something. But we need to meet a lot more often. All right. Okay. Bye bye. Yeah. So. Yeah, you'll be. You guys can Skype in. You don't have to come for it. Just I'm gonna keep it very simple to the point, and then there's gonna be a lot of work after that, which you guys will be working with Yvette, who will be our program coordinator, who's our program director. Bye. Happy New Year.